Now variable capital omega and I together locate the orbital plane with respect to the equatorial plane. To locate the orbital coordinate system with respect to the equatorial coordinate system, we need omega, which is called the argument of perigee west. So this omega is actually the argument of perigee. So this is the angle measured along the orbit from the ascending node to the perigee point. Now what time we use for satellite system? So that particular time is called the universal time. Sometimes it is also called the Zulu time. So it is basically the mean solar time at the Greenwich Observatory near London, England. Okay. Sometimes it's called the UTC. So in any satellite communication system, you see that the time that is given in the satellite signal, that is basically the UTC time, right? And we have to get the local time from the UTC time using some simple formula. To specify the absolute coordinates of the satellite at time t, we need to know 6 quantities that we have already mentioned. These quantities are called the orbital elements. So we can select 6 orbital elements like this: eccentricity, semi-major axis, that is A, time of perigee, Tp, right ascension of ascending node, capital omega, inclination angle or inclination I, argument of perigee, that is small omega. So these are the 6 orbital elements. That means if we know all these 6 parameters, we can easily specify the orbit of a satellite and we can locate the satellite in the orbit. Let us try to solve one numerical problem. The Earth rotates once per sidereal day. The value is given. Show that the radius of the geo is this one. Very simple problem. So we have already derived this equation, t square equal to 4 pi square a cube divided by mu. So a cube can be written in this way. We can calculate the time in second, right? From this given time, it is nearly 86,164.09 seconds. So just put those values. This is standard value. Mu has got standard value. So if you calculate, you will see that A is nearly equal to 42,000 kilometer. It's a very simple problem. Let us try to solve another problem. A space shuttle is an example of low Earth orbit satellite. Sometimes its orbit at an altitude of 250 km above the Earth's surface, where there is still a finite number of molecules from the atmosphere. The mean Earth's radius is approximately 6378.14 km. Using these figures, calculate the period of the shuttle orbit when the altitude is 250 km and the orbit is circular. Find also the linear velocity of the shuttle along its orbit. So let us try to solve this problem. First of all, we have to calculate the radius of the orbit. So height is given 250 km and average radius of Earth is this one. So average radius of the orbit will be height plus the radius of the Earth, that is this one. So using t square equal to 4 pi square a cube divided by mu, this expression, putting the value of a, we can calculate the expression for or value of the time period, right? So this orbit period is about as small as possible. At the lower altitude, friction with the Earth's atmosphere will quickly slow the shuttle down and it will return to the Earth. So all spacecraft in stable or Earth orbit have orbital periods exceeding 89 minutes 30 seconds. The circumference of the orbit that we can calculate 2 pi a equal to this one. So velocity of the shuttle in the orbit will be the circumference divided by the time period of revolution. Okay, and it turns out to be nearly 7.7 kilometer per second. So this is the velocity of the shuttle at a height of nearly 250 kilometer above the Earth's surface. The subsatellite point is the location on the surface of the Earth that lies directly between the satellite and the center of the Earth. Actually, subsatellite point plays an important role for geostationary satellites because for geostationary satellite, the subsatellite point is fixed. If we consider LEO satellite or MEO satellite, their position with respect to Earth's surface is changing all the time, right? So for all those satellites, LEO satellite or MEO satellites, the subsatellite point is not a fixed point. It changes its position. Changes position. So subsatellite point is very important for geostationary satellite. It is the nadir pointing direction from the satellite, and for the satellite in an equatorial orbit, it will always be located on the equator. So to an observer of a satellite standing at the subsatellite point, the satellite will appear to be directly overhead in the zenith direction from the observing location. The zenith and the nadir paths are therefore in the opposite direction along the same path. Okay, so this is the nadir direction, and from this point, this is the zenith direction. Now, how we can locate the satellite from some Earth station? Okay, and for that we require two angles. One is called the azimuth angle, another is called the elevation angle, right? So suppose this is the local vertical. We are standing at some point and this is the local vertical. So this is the east direction and this is the north direction. Okay. Now to locate the position of the satellite from this point, we require two angles. One is the azimuth angle that is measured from the north direction in the horizontal plane, right? And another angle is the angle measured in the vertical direction from the local horizon. Okay, so this angle, this is called the elevation angle. So earth station antenna designers do not reference their pointing direction to zenith. They use the local horizon plane at the earth station to define elevation angle, and the geographic compass points to define azimuth angle, thus giving the two look angles for the earth station antenna towards the satellite. So AZ and EL, azimuth angle and the elevation angle. If we know the azimuth angle and elevation angle from a particular location for a satellite, we can uh, easily direct the receiving antenna towards the satellite and we can get the signal. Otherwise, it will be difficult for us to locate it. Okay, we can easily calculate the azimuth and elevation angle by knowing the location of the satellite and knowing the latitude and longitude of the local point. Okay.